Everything you've been told about getting to Mars is already outdated. Scientists just mapped a route through space that nobody considered seriously before. And it doesn't just cut the journey shorter, it changes the entire logic of how humans travel between planets. Here is the problem with Mars as we currently approach it. The conventional route to Mars, using what's called a Hohmann transfer orbit, the standard energy-efficient path spacecraft have used for decades, takes between 6 and 9 months depending on where Earth and Mars are in their orbits. That window only opens once every 26 months. Miss it and you wait over 2 years for the next one. For a robotic probe, that's inconvenient. For a human crew, that 6 to 9 month journey is genuinely dangerous in ways most people don't fully appreciate. Deep space radiation exposure during transit is one of the most serious unresolved threats to human Mars missions. Outside Earth's protective magnetic field, astronauts are bombarded by galactic cosmic rays and solar energetic particles. A 6 to 9 month one-way trip means a crew absorbs radiation doses that significantly exceed NASA's current career exposure limits before they've even landed. Add the return journey and you have a radiation problem that no existing shielding technology has fully solved. Time in transit is not just an inconvenience. It is a medical emergency waiting to happen. This is why what researchers are now seriously investigating changes the equation entirely. The concept gaining real scientific momentum is called a low-energy ballistic lunar transfer, combined with Sun-Earth and Earth-Mars Lagrange point navigation, what some researchers are calling the Interplanetary Transport Network, or the gravitational superhighway. This isn't new theoretical physics. The mathematics behind it has existed since the 1990s. But the computational power needed to actually map practical human mission trajectories through this network has only recently become available. Here is how it works without the jargon. The solar system is filled with invisible gravitational pathways created by the interacting pull of the sun, planets, and moons. Objects moving along these pathways require almost no fuel to travel enormous distances, because they are essentially riding gravitational currents, the same way a surfer rides a wave rather than swimming against water. Spacecraft can be nudged into these corridors and carried along them with minimal propulsion. The trade-off historically was time. These routes were slower. But new trajectory modeling, particularly research published through institutions including NASA's Jet Propulsion Laboratory and work building on ESA mission data, is revealing optimized corridors that are far more time competitive than previously calculated. And then there is the propulsion side of this discovery. In parallel, NASA's ongoing investment in solar electric propulsion and the continued development of nuclear thermal propulsion is fundamentally changing what faster transit could look like. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant and expel it for thrust, has been theoretically capable of cutting Mars transit time to roughly 3 to 4 months for decades. NASA's current Draco program, the demonstration rocket for agile cislunar operations, is actively developing nuclear thermal propulsion technology with a planned in-space demonstration targeting the late 2020s. This is not a concept paper. This is a funded, active program with a timeline. When you combine gravitational superhighway trajectory optimization with nuclear thermal propulsion capability, the theoretical pathway to a 45 to 90-day Mars transit begins to emerge from the math. Researchers at the University of Colorado and teams connected to JPL have been running trajectory models exploring exactly this combination. The results are not yet a confirmed mission plan, but they are serious enough that they are shaping how NASA and private space companies are thinking about crewed Mars architecture for the 2030s and 2040s. SpaceX's Starship, which completed its fourth integrated flight test in June 2024, is designed with Mars in mind but still relies on conventional chemical propulsion, meaning Elon Musk's current Mars timeline still involves those 6 to 9 month journeys. The faster route isn't Starship's path. It belongs to whoever masters the combination of gravitational navigation and advanced propulsion first. The stakes here are not abstract. Every month shaved off a Mars transit is a month less radiation exposure, less muscle and bone degradation from microgravity, less psychological strain on crew, and less food, water, and oxygen that needs to be carried. Shorter transit times don't just make Mars more reachable. They make human survival on the journey statistically more likely. We are not yet sending humans to Mars, but the route they will eventually take is being drawn right now, and it looks nothing like what anyone imagined 20 years ago. The universe gave us gravitational highways billions of years before we had the mathematics to find them. Now that we've found them, the only question is who gets there first, and whether we'll be ready when they do. If you could choose between a 7-month chemical propulsion journey or a 45-day nuclear-powered transit to Mars? Which risk would you rather take, and do you think we'll actually make it there before 2050? Follow for more science that is actively reshaping the future of human exploration.